Yeah, so I'm Osbert Bastani, and first I'd like to thank the organizers for hosting this workshop and for inviting me. And today I'm going to be talking about some of the work my group has been doing on trying to leverage a technique called program synthesis for interpretable machine learning. And to kind of motivate why I think program synthesis is a useful tool, I'd like to start from this age-old question of what is interpretability. So typically, if we're thinking about interpretability, we have some kind of question or task that we're trying to solve or understand. So here I'm showing an example of an RNA splicing task, which I'll say a little more about later. And then we try and use machine learning to predict some aspect of this task. So for example, you might train a deep neural network to try and predict some kind of labels in this domain. And then the hope is that a scientist or a human can look at this neural network or whatever model you've trained and gain some insight from it. Beyond just kind of the raw predictions that the model produces. And for this to work, the human has to be able to understand the model. So that's kind of what a lot of the traditional interpretability literature is focused on. You know, we have to be able to know what the model means. But there's also a really important aspect, which I think doesn't get as much attention, which is that the model also has to be, it has to accurately reflect the true underlying mechanism, whatever that might be. So just to kind of give a little bit more motivation, specifically in this RNA splicing domain. So this is a domain we've kind of been looking at recently. And the basic idea here is that it's a step in RNA translation. So when you're taking RNA and you're translating it into a protein in your cells, before that happens, there's a biological process that occurs where portions of the RNA known as introns are spliced out and removed to form the final RNA sequence that gets translated to a protein. And there's a biological mechanism by which this happens. And our understanding of this mechanism is that there are some proteins that bind to the RNA sequence. And then if the right combination of proteins binds in a certain segment of RNA, then there's going to be a chemical reaction that causes the splicing to occur. And then these proteins will kind of go down and splice all of the introns from the from the RNA sequence to form the final sequence. So here, there's kind of this very clear underlying mechanism that scientists would like to understand better. And there's a lot of reasons for wanting to understand this. For example, if we understand how the mechanism works, we might be able to come up with therapies to treat diseases that are caused by mutations that affect splicing. But the current machine learning approach to the problem is to just train an end-to-end predictive model to decide whether a given point in the sequence is a splice site or not. So basically, your input to the model is going to be a sequence of RNA bases, and the output is whether some base in this sequence is a splice site. And if you train a neural network on this task, you can get really high accuracy. So Splice AI is probably state of the art here. It's a deep convolutional neural network that's designed to solve this task. And I think it achieves something like 95% top one accuracy, which is very impressive. But it's largely a black box. So there's very little insight into the splicing mechanism. You can get a little bit of insight by doing perturbation analysis and things like that, but you can't really look at the model and understand anything that it's doing. So obviously, we all know that interpretability is really important for these kinds of problems. But the challenge is that if you look at most existing interpretable model families, so things like linear models or decision trees, they're not really designed to capture this splicing mechanism, right? It's not a linear function of the input sequence or even really a decision tree. It's a much more complicated computation that's going on to cause splicing to happen. So if you train these naive interpretable models on this task, you're still going to get very low accuracy, and you're not going to get any insight because the models just aren't reflecting the true underlying mechanism. And so there has been a lot of work on kind of interpretable machine learning in this space, but it's largely focused on very handcrafted models thus far. So people will try to train parts to do different tasks that they know how to solve, and then try to kind of piece these parts together in order to get an understanding of what's going on. And really, I think what this motivates is the need to design, to give scientists a way to design model families that capture underlying mechanisms in physical processes. So that's kind of one example from science, applications of machine learning to science. Actually, a lot of the work that my group has been doing so far has been more in terms of control and reinforcement learning, but I think the same kinds of issues arise. So just to kind of give one example, we looked at this parallel parking task where I'm sure most of you know how to parallel park. Here you're actually trying to exit from between two black cars. So you imagine you're the car in between the two black ones and you're trying to get out. And there's this kind of very natural and generalizable strategy that you can use, which is to kind of go forward a bit and then back up a bit, go forward a bit, and do this back and forth motion. And then finally you can, once you've done that enough times, you can exit the parking spot. And depending on how far apart the two black cars are, you might need to go back and forth a very large or very small number of times. But if you just train a neural network to try and solve this task, so if you train it on, and then you test it on an example from the same distribution, it'll actually work pretty well. It does capture this kind of back and forth motion. But then if you change the problem parameters a bit, for example, we move the two black cars more close together, then all of a sudden the neural network is not going to work very well. And again, I think what this represents is that the neural network hasn't kind of learned the true policy in some sense, one that solves the task in a very generalizable way across many different problem settings. Instead, it's kind of fit some specialized, some kind of strategy that's specialized to the distribution of inputs that it sees during training. And again, I think this motivates the question, can we design a policy family that we can learn where the policies come from some class that captures this kind of back and forth repeating motion. So really, I think this repeating motion is characteristic of many control tasks that you see in practice. So, so that's kind of motivating why I think we really need model families that can capture mechanisms in like some kind of true mechanism in a target domain. So for example, the bind then splice mechanism, as well as this repeating motion in control. And the question is, how do we actually achieve this? So basically, I think there are two properties that a model family needs to satisfy, or at least that are sufficient for a model family to satisfy for this to be possible. So I am kind of making an implicit assumption that there is some underlying true mechanism that we're trying to discover here. Assuming such a mechanism exists, then the model family first needs to be realizable. So it has to contain the true mechanism, right? If the true mechanism isn't even in the model family, then there's no way we can learn it. And the other aspect is that it has to be identifiable. So we have to be able to identify the best, given enough data, we need to be able to find this model. It's not useful for a model to exist if we can't ever find it, even given a lot of data. So just to kind of illustrate the two things that can go wrong, if we choose our model family to be too small in some sense, it's not going to be realizable because it won't contain the true model. But if we choose it to be too large, for example, we choose a non-parametric model family, or oftentimes neural networks also kind of fall under this umbrella. If we choose it to be too large, then it's going to be really hard to actually find the true model. So that's the trade-off that we're trying, and then the model family is not going to be identifiable. And this is the trade-off that we want to enable users to balance for their target domains. So just to kind of, if we think about some of the classical interpretable model families, so things like linear models are very easy to identify. They don't have too many parameters, and you can actually characterize the sample complexity. But oftentimes, they're not going to be realizable. You can sometimes alleviate this by doing feature engineering, but in the general case, you're going to need a very large number of features to achieve this goal. On the other end of the spectrum, we have decision trees, and at least if you grow them to be large enough, we know that these are non-parametric model families. So if you have sufficient depth in your decision tree, then it will be realizable. The interpretability then becomes a little questionable, but at least you could represent the true mechanism with enough data. But it's very hard to identify because you're going to be looking at an exponentially complicated model, and you're going to need a huge amount of data in order to identify the kind of true decision tree in some sense. So what we really want is to be able to design model families that are tailored to the specific domain instead of just using kind of a generic off-the-shelf model family. And I think this is something that program synthesis has the potential to achieve. I will say that I think there's a parallel here with deep learning, because if you think about deep learning, one of the strong suits of deep learning is that it does have this flexibility in letting you design complicated model architectures. The problem there is that they're not interpretable. So another way to think about it is whether we can come up with an interpretable analog of the kind of deep learning frameworks. And that, I think, is the goal of applying program synthesis to machine learning. So we've already talked about tailoring the model family. And the strategy is program synthesis. Okay, but I haven't told you yet what program synthesis is. I'm going to give a fairly high-level overview, and later I think I'm going to go through a couple of different projects that we've worked on in this space that I hope will give you a better sense of what the kind of available techniques are. So just to kind of, it's actually very closely a set of techniques that are very similar, at least at an abstract level, to machine learning. In machine learning, generally, you are given some data Z, for example, XY pairs, and then you want to feed it to a machine learning algorithm, for example, a linear regression algorithm, and then you get out a model F, for example, a linear model. Program synthesis is basically the same, but we have this little extra flexibility at the beginning. So typically, our data consists of input-output examples. So for example, I might give you, again, a bunch of XY pairs. But now the user also has to provide a domain-specific language. So I'll say a little bit more about what exactly that is, but basically it encodes a search space over programs. So it's a context-free grammar that encodes a kind of very structured search space over programs that form your model family. And then once you have these two, you feed them to a program synthesis algorithm, which basically it's the same as a machine learning algorithm. It performs some kind of search over the space of programs to find one that best fits the data. And then finally, it'll output that program. So the space of programs is determined by this domain-specific language, or DSL, called G. And it's really this, it's really the first step, this design of the domain-specific language that gives us the flexibility to design the model family. And just kind of formally, it's a context-free grammar where the productions in the grammar encode constructs designed to capture computations that are relevant to the domain. It doesn't matter too much. I'll give some examples of programs later in the talk that I think will make it more clear. And then the second step is the kind of learning step where you search over programs in the DSL to find the optimal one. So typical search strategies include things like enumerative or stochastic search, which are similar to what you might use to find things like optimal rule lists or decision trees. So that's the kind of program synthesis in a nutshell. So originally, program synthesis was kind of targeted at traditional programming tasks. So actually, one of the most widely used program synthesis frameworks is for synthesizing Excel formulas. So you have a column of data, and you just give it an example of how you want it to transform that column. Maybe you're adding two numbers together. Maybe you're doing some basic string processing. And you just give it one or two examples, and it'll synthesize a program and apply it to the rest of your data. And if you've ever used Excel, this is actually implemented there in a tool called FlashFill. So that's kind of the very most basic example of program synthesis. Here we're interested in applying it to interpretable machine learning. And just to kind of give a sense of some of the families that you can design. So for the RNA splicing work, that's actually something ongoing that I'll, if I have time at the end, I'll loop back to it. But there we have these, we're designing these kind of modular programs that can basically lets you kind of separate the protein binding phase from the splicing phase, as I illustrated at the very beginning, to kind of reflect our understanding of how splicing works. And then in the control domain, we had this repeating, kind of back and forth repeating motion that we wanted to capture. And in general, you might design programs that have kind of are if-then-else rules, but have finite state. So like a rule list, but with some kind of finite state that lets it keep track of which mode it's in. And we'll go into that. I'll show an example of that in a minute. So the kind of very simplest domain for applying program synthesis is in supervised learning. So here we've done some work on synthesis for supervised learning tasks. So just to kind of illustrate some of the use cases. So one application we've looked at is web question answering. And in this domain, we have basically the programs look like the following. First, so they're actually going to include neural networks as components in this case. And basically you apply a neural network. So you start out with some kind of a web page, and you might want to scrape like some information from the web page. For example, what program committees this person has sat on, so that, and then you can go and scrape a bunch of faculty web pages to compile a list of this data. So that's the goal. And the challenge here is that there's a lot of, people use different terms for professional service, and it's structured in different ways on the web page. So the idea is that you first apply a neural network to extract relationships. So maybe you have some keyword that you want to identify, but you don't want to do it exactly. So maybe you have service and you want to look for phrases that kind of match service. So you first apply a neural network, and you can get similarity scores between, so that's one construct in the domain-specific language. So then this neural network kind of represents those similarity scores. And then you might have rule lists that kind of filter information based on the predictions of these neural networks. And then once you have that, and there are also other constructs. So for example, if things to process lists like map and filter, and so on. And then once you have, then you synthesize a program in this language, and you can get some list of the service that the person has been a part of as the output. Just to kind of highlight some results in this domain. So we built a synthesizer for this, we built this DSL for this domain, and applied synthesis to it, and we showed that, so one kind of additional advantage, which I didn't highlight earlier, but you can also often learn programs from very few examples. So here, this is a few-shot learning task. I think we just give it 6 examples, input-output examples, and you're able to get a very, very good F1 score compared to, say, a deep learning baseline or other kind of traditional ML-based approaches. And we've also, just to give another example, we've also been applying program synthesis to devise queries over video trajectories. So in this is another supervised learning problem where we're basically using a neural network to, so we have a bunch of video data, and we want to identify some patterns in the data. So here, this is a traffic camera, and we want to maybe look for cars that are turning from one lane into another lane. And then we can synthesize queries that look like the following one. So in this case, the programs have the space kind of look like regular expressions, but they're generalized to apply to real valued sequences instead of just strings. And then you can synthesize a program in this language, and you can select kind of all of the cars that are turning from this lane up here to this lane over here. And as you can see, this program is kind of fairly easy to interpret. It says that the car has to be, we want to synthesize trajectories that start in, so this is lane 1, so that start in lane 1, and then they can do something in the middle, and then they end up in, oh, that should be lane 2 here. Sorry for the mistake. So yeah, they end up in lane 2, and then they continue on their way. So yeah, those are some examples from supervised learning. As I mentioned earlier, a lot of the work that my group has been doing is more in the reinforcement learning and control domain. And I think this is, so here there's a lot of tasks that people are interested in applying reinforcement learning to, things like self-driving cars, robots, and so on. And there's a really important kind, so there are additional benefits that actually come from programmatic, having programmatic control policies in these settings. So beyond just interpretability, you want the user to be able to look at the policy and make sure that it kind of is doing the right thing, but it also has advantages like they tend to generalize better off distribution. So that's one thing I alluded to earlier. And the idea is that, so just to kind of, at a very abstract level, the goal of deep reinforcement learning is to take a control problem and learn a neural network policy to solve that problem. For example, so typically this policy will take in a state encoding, a vector encoding the state of the system. So here I'm thinking about Pong in the kind of abstract representation where we have the positions of the balls and the ball and the paddles. And then feed that to a policy and then output a set of control actions to take in that state. And then we're going to kind of iterate this process over some horizon in order to optimize some reward. And the problem, so we actually have very good algorithms for training neural networks in these settings to solve these kinds of tasks. But the problem is, of course, that they're not interpretable. And our goal is to try and learn an interpretable programmatic policy to solve these tasks. The challenge here, which I think makes the reinforcement learning setting particularly interesting, is that program synthesis algorithms are typically designed to target supervised learning problems. Actually we don't have good algorithms for solving program synthesis in the reinforcement learning setting where you're trying to maximize the reward over some horizon. So we've actually been doing a lot of work on reducing this this reinforcement learning problem to a supervised learning problem. So the kind of basic strategy is that you can use reinforcement learning to train the neural network control policy, and then this reduces the learning problem to a supervised learning problem via a technique known as imitation learning. Basically, we can use the neural network to generate labeled states and then use that to train the programmatic policy using your favorite program synthesis algorithm. So imitation learning is this technique from, it was originally motivated by this idea that we want, if you have a human expert who knows how to solve some task, for example, flying a toy airplane, you can have them provide a bunch of demonstrations and then try and distill these demonstrations into a control policy. So basically, we're just going to take this idea and we'll replace the human with the neural network that we trained. So we'll use deep reinforcement learning to train a neural network, and that'll be the kind of human expert. And then our goal is to kind of use this to distill a programmatic policy. It's a pretty straightforward approach. Basically, once you have the neural network, you're going to use it to generate a bunch of states. So you use it to play the control problem. You have it, for example, play this game of Pong. And then you just use it to, so now you have a bunch of X's and you use it to label the optimal action in each of these states, and now you have a bunch of Y's, and now you can use supervised learning to train to synthesize a program. So there is kind of an important caveat, which is there is this distribution shift problem if you're familiar with imitation learning. So typically there's a feedback loop where you then kind of use the decision tree or whatever programmatic policy you've trained in order to generate more states, and you kind of repeatedly train it in this way. So this is kind of state of the art in imitation learning. So you could just take this and actually apply it to our program synthesis problem. But we actually found that there's a kind of a shortcoming of these existing approaches that we can exploit to do better. And the basic problem is that they kind of treat all state action pairs the same. So if you think about, so this is a toy game of Pong I'm showing, a toy version of the toy game of Pong I'm showing here. So we have basically a ball that's bouncing around, and you can move the paddle back and forth in order to try and keep it in the game arena. Basically, if you look at the state on the right-hand side, there it doesn't really matter what action you take. But if you look at the state on the right-hand side, we really need to move the paddle to the right to avoid losing. So that's what we call a critical state. And the problem is that this existing imitation learning approach, which is called DAgger, I forgot to mention, but this existing imitation learning approach kind of treats all of these states similarly. It doesn't really distinguish between the left and right states. And this is fine if you're trying to train a neural network, because a neural network will just learn everywhere. But if you're trying to train a programmatic policy, you really want it, because it has much more limited model capacity, you really want to focus its attention or its kind of model capacity on critical states. So our approach, our kind of solution is to leverage the Q function. So this is also a nice thing we have in our setting that you wouldn't have in the traditional imitation learning setting. So if you train a neural network policy, you usually also get a Q function out of that if you, say, use actor critic. And basically, the Q function says, encodes how good an action A is in a state S as a real number. And so, yeah, this is something we just take for granted. It's a neural network typically that we just have off the shelf. And basically, if you have a non-critical state, we can just look at the Q function and figure this out, because the Q values for the different actions will be pretty similar. So the worst and best case actions aren't too different in terms of their Q value. But if you look at a critical state, you have a big gap in the best and worst case Q values because the action you're taking really matters. So we can use this characterization of critical states in order to improve our algorithm. And basically the idea is that whereas DAgger treats all state action pairs equally, so that's just the standard 0-1 loss from supervised learning, our algorithm, which we call Viper, weights state action pairs by the Q function difference. And it turns out basically what you do is you take the optimal Q value, you subtract off the worst case Q value, and you use that as a weight. So this will upweight critical states when you're learning your policy. And it turns out that you can actually theoretically characterize that this is in some sense the right thing to do. So we can get tighter bounds. I'm not going to go into the details of this theorem, but you can actually get tighter bounds compared to the original DAgger algorithm. So yeah, I think I didn't include the plot, but we actually can show that we get much small. So if we're just thinking about learning decision trees, we also showed empirically that by using Viper, we can get much smaller and compact decision tree policies compared to something like just using vanilla DAgger. So just kind of, but coming back to interpretability, so we've used this on a toy game of Pong. The question is whether, now that we're learning these controllers, these programmatic control policies, whether or not they're interpretable. So to start off with, we were just thinking about using vanilla decision tree models. So even kind of, you can also use this framework to learn traditional interpretable models such as decision trees. In this setting, we looked at a toy game of Pong, and we fed it to we trained a neural network to solve that task using deep reinforcement learning. And we extracted a fairly compact decision tree using our Viper algorithm. And one nice thing is we could actually prove that this decision tree controller was correct, so that it never really lost this game. It could continue to keep the ball forever. So that's one in the arena forever. And I think this is a nice, interpretability has other payoffs. But beyond just being able to, for a human to look at it, you can actually also formally analyze it using a computer much more easily. I'm not going to go into too much detail, but the high-level strategy is that you can basically formulate this idea that if the ball starts in the blue, then if you think about, so the dynamics for this thing are actually piecewise linear, and if you have a decision tree control policy, it's also a piecewise linear thing. So you can actually basically encode this correctness property that what you need to prove is this invariant that if you start in the blue region, then you come back to the blue region after some number of steps, right? If you prove that, then by induction, you're going to be kind of play the game correctly forever. And you can encode this correctness property as basically an integer linear program that you can solve very efficiently. We actually did find a bug in the decision tree when we first tried this. So there's this error, this bad state where if the ball starts at the very left-hand side of the right-hand side of the screen, then the decision tree will actually make a mistake and it won't kind of keep the ball in the arena. But kind of a testament to the interpretability of the policy, we were able to fix this by manually editing the controller. So we went into the controller and we found the condition that we needed to change. And then after that, we actually proved that the resulting controller is correct. So this kind of shows that these interpretable policies do have these benefits where a human can go and kind of fix issues with them. Okay, but that's kind of a traditional interpretable policy. Earlier I had this motivation of a kind of more complex control problem where you have this back and forth motion. So can we use these ideas to solve this problem? And of course, the answer is yes. So here for the parallel parking task, we have this notion of a state machine policy. And basically what the state machine policy looks like is it has a small number of modes. So here on the right-hand side, I'm showing a policy which has 3 modes. And you can think of this also as basically being a bunch of if-then-else statements where the condition is which mode you're currently in. And basically in each mode, the control policy is very simple. It's just a linear function of the state. So for example, the first mode is the green part. So that's the part that kind of tells you to drive forward and to the left. The second mode is the red part. Let me see if I can. Yeah, so this mode is the one that tells you to then back up and go to the right. And then finally, the third mode is after you've kind of done this back and forth loop, you can go and drive to your goal directly. So that's this blue mode over here. And as you can see, the state machine has this loop where it's going to go back and forth. So these things on the edges are guards. So there's also a mode transition part of the program that tells you how the mode changes at each step. So first, once you're almost about to hit the car in front of you, then you can transition to the next mode. And then same conversely for when you're going backwards. And then finally, once you're kind of far away from the 2 black cars, then you transition to this last mode. And then you can finish the task. So that's that's our DSL for this example. So we have this DSL of state machine policies, and we use a similar imitation learning strategy that I just described in order to train these models. It is a little bit more challenging because actually if you try to mimic a neural network in this case, it doesn't do that well. And the basic problem is that if you have a neural network, it's going to be, as I say, it doesn't actually find the true mechanism. So you can't really expect to distill it into some program that has a true mechanism, right? So we actually use a teacher whose structure mirrors that of the student to solve this problem. So our teacher it's kind of like the student, but it's a lot easier to learn. And then we kind of condense the teacher into a student. So what do I mean by that? Well, basically the teacher is, the thing I showed you has just 3 modes, and basically you switch back and forth between those modes. But the teacher is kind of like a linear sequence of modes. So you give it a lot more modes for it to work with. And then you can actually train these policies pretty easily using gradient descent, things like policy gradient. So you train a teacher of this form, and then you basically condense it into a student. So that's the kind of synthesis step. Is you search over the space of these kind of state machine models and find the one that kind of best approximates the teacher. And there's also actually a back and forth, so we can then retrain the teacher to kind of better fit based on our current student to get a better teacher. But yeah, this is the basic idea behind our algorithm in this setting. So we can learn these really nice state machine policies. I've already shown one for the parallel parking task. Basically, one nice thing to just, again, kind of come back to this question of interpretability. Again, we can actually validate interpretability by kind of manually looking at the state machine policy that it learns and tweaking it to significantly improve its performance. So it does correctly solve the task, but we can actually get it to solve the task faster by making some small modifications. And we can also kind of solve more challenging tasks. For example, for the Mujoko swimmer, we got a policy that has this nice kind of swimming motion that's, again, a repeating task, right? Swimming is a repeating task, and we're able to synthesize a control policy to capture this repeating motion. So that's kind of one example from control. We've also kind of been working in the multi-agent reinforcement learning setting. So this is a very different problem, but again, I think we can, we can use program synthesis to learn more interpretable control policies. In this case, the kind of complexity comes not from the kind of repeating structure of the task, but the fact that we have a very large number of agents. And in fact, it might even be a variable number of agents, right? So we have some space of agents, and we want to learn a policy for them to kind of coordinate in order to solve some tasks. So the policy should take in this kind of complicated representation of the state and output a control input for each of the agents to take. So the biggest challenge here is that you have this very complex high-dimensional state space that consists of all of the agents currently in the system. And importantly, we're interested in the decentralized control setting. So it's not like we have one agent telling everyone else what to do. They actually have to communicate with one another in order to figure that out and make decisions. So just to illustrate the task that we're trying to solve, so we have this group of agents that's trying to get to its goal. This is a really simple example. There's just one group of agents, and they're kind of, they can all talk to each other and coordinate to avoid bumping into each other while they get to their respective goals. But it quickly becomes more complicated when you have different groups of agents with potentially competing goals. So for example, here, all of these agents have to get to their goal without bumping into each other. So you have this effect, for example, where the purple agents kind of linger around a bit at the beginning, to wait for the blue and green agents to pass, and then before they move to their goal. So one kind of basic strategy for solving this problem is to do so it's a multi-agent reinforcement learning problem, but the main question is how do you represent the policy? So if you're using deep learning, you can construct these graph neural network policies where the edges in the graph represent communication. So if you have basically message passing, so you have if you're familiar with graph neural networks, you pass messages between kind of nodes in your graph, and that's kind of how you achieve communication. But here, the structure of the graph has to be fixed by the human. So when you're designing this approach, you say, okay, each agent is going to have 5 neighbors, and that's how we're going to solve the problem. Actually one of the important things is we want to be able to learn the communication structure. So if we try and do that, then basically now one way to do that, so we don't want to fix the graph ahead of time. We actually want to kind of each agent to learn who they have to communicate to. So one way we can fix this is by instead using a transformer as the control policy. So basically you have attention over all of the other agents. And again, so you're still passing these messages between agents as the kind of communication strategy, but the structure of how they pass these messages is encoded via the soft attention mechanism. The problem is that if you do this, you're basically going to get these soft attention weights which aren't very interpretable. So when we had the graph, it was this manual thing, but at least we could understand how agents were communicating. But here you get this kind of very dense communication structure. So here the purple agent is talking to almost all of the other agents in order to solve the task. Lack of interpretability is an important shortcoming, but there are also others. For example, lack of robustness, and also communication costs. So this might cost a lot of bandwidth. And one idea is to instead try and learn a sparse communication graph by using programmatic attention. So here we're only using program synthesis, to learn the structure of the communication. So the rest of the policy is still going to be a neural network. Yeah, and I think just in interest of time, I'm going to kind of go through the strategy a little quickly. So we have a program that's deciding which other agents in the system to talk to, and then you get some control inputs out. Yeah, so, but then you actually use a neural network at the end to get once you've decided a small number of other agents to talk to, you use a neural network in order to get the control inputs out of for each agent. And it's basically the same imitation learning strategy where we use imitation learning to train a programmatic attention policy. And in this case, we're doing stochastic search over the space of possible programs in order to minimize this objective. So there's an added penalty here for the maximum degree of the communication graph because we want to kind of keep the communication sparse. And we get these really nice interpretable rules. So here, basically, this is the same task I showed earlier, and this is so basically this pink agent is now only talking to 2 other agents. The first rule is that, and there's one rule for choosing each other agent to talk to, and the first rule is basically filtering out all of the, so it starts with this list of all of the other agents, and then we have this filter operator in our domain-specific language that basically randomly chooses one of the agents in this orange region. The orange region is determined by some linear constraint on the state space. And then once you've filtered out, you randomly select one of the agents in this orange region. And basically what this encodes is the intuition that you want to talk to one of the other agents that's kind of between you and your goal. So that's the first rule, and you can see that it's actually adaptive. So if we reverse the goals, so now the green agents want to go in the other direction, now we're going to get communication. Now it's going to communicate with one of the agents, the orange agents instead. So it is a kind of flexible policy that can adapt to the current task that's to be solved. The second rule, so that's kind of communication with a different group of agents. The second rule is a bit simpler. You're just communicating with basically the closest agent. So here, basically, you're computing the distance to every other agent and the negative distance to every other agent. And then you have this argmax operator in your domain-specific language that captures the idea that you want to choose the agent that maximizes some metric. So that's going to be the closest agent. So as you can see, you get these really nice interpretable communication policies out of the synthesis algorithm. And you can kind of understand what the agents are doing in order to solve the task. And just to kind of one last thing to know is we also get these nice sparse communication structures. So if you look at the transformer, even if you threshold the attention, you have this very dense communication, but using R's, each agent is only talking to a very small number of other agents. That's a lot of the work we've been doing in control and reinforcement learning. I just wanted to take a minute or two to kind of loop back to this modular neural networks for splicing example that I started off with. So this is actually ongoing work, but we're pretty excited about it because it's kind of I think it's a really nice demonstration of some of the, how these ideas of program synthesis can be useful in interpretability. So as I mentioned at the beginning, we're looking at this splicing mechanism where you have an RNA sequence, and you have some kind of binding and interactions between proteins, and then finally you get out this splicing model at the end. And Splice AI is this end-to-end neural network that predicts splicing, whereas we're working on basically this modular network. So it's actually a little bit of a hybrid between the deep learning and the program synthesis approach. We're basically designing smaller modules, but based on so each module is a neural network and it's designed to solve some task, but then we're trying to piece these together in order to solve the task end to end. And basically these modules, one of the most important things that were kind of interesting ideas that we had here is that so you can design these modules in isolation, but they don't necessarily communicate with each other very well. So, or in interpretable ways. For example, if you just kind of build this module and you train it end to end, you're going to get that it's going to learn a very uninterpretable basically, it'll just say that a lot of things are binding in random places, and you won't get very interpretable binding sites. So what we do is we actually have a sparsity penalty here in order to encourage it to learn sparse binding sites. So we have this constraint saying that it can only bind some fraction of only some fraction, each protein can only bind on a small fraction of the RNA sequence to prevent it from just saying that the protein binds everywhere. And then once we have these nice sparse binding patterns, then we feed those down to the downstream splice predictor. And right now the splice predictor is just a giant neural network, but we are trying to also work on making that part more interpretable. We have quantitative results. So our approach is this one on the very right-hand side, and it's not quite as good as Splice AI, but as you can see, it still does quite well, especially if you compare it to some of the more traditional handcrafted models I mentioned at the beginning, which perform substantially worse. And the important thing is we do get these nice interpretable intermediate binding patterns. So you can see that the proteins bind to the RNA sequence at various points, and we can actually identify which ones are, at least according to our model, most responsible for splicing. So ongoing work, we're still trying to understand exactly how well these things actually correspond to the real splicing mechanism, but we have some promising results in that direction as well. So just to conclude, I think program synthesis gives us a really flexible way for designing model families that are interpretable while still being able to learn the true mechanism, which really gives us end-to-end interpretability, not just of the model, but enables us to get insights into the underlying task. Thanks for listening. I'm happy to take any questions.